So, so I was going to go over just the practice exam that's in the D2L folder. What can I say about it? The format is going to be very similar to the last exam. It's going to cover pretty much from conductivity 7B on. So I'm not going to focus on anything specific from earlier sections, but and I mean earlier, like the order we did it in. So we did do conductivity 4 and 5, I think, afterwards, or whatever number it started off at. But everything's cumulative anyway, so you still expected to know Coulomb's law and how to talk about it a little bit. You'll need some of that information in order to explain. I mean, you saw in the quiz, in order to explain some of the answers. So, for instance, why is sodium's ionization energy so low? Well, sodium has shell 3, has 1 electron in shell 3, whereas neon has only up to the 2nd shell filled. And a lot of people gave me the answer, oh, the neon shell is filled, that's why it's higher. No, well, that doesn't explain why the ionization energy for sodium is lower. And that's because the shell 3 electron is further away. And you're welcome to use Coulomb's law to kind of explain how it's less attractive because it's further away. Some people took a step further and used the core charge model to explain that the valence electron is being held on with a +1 core charge versus a +8 core charge for the neon. And that's not exactly what I was looking for, but that works too. That was a good enough explanation for why the ionization energies are so different. So make sure you know all that stuff. All right, so you can see that pretty much the same things are going to be given to you. We've got the Bohr/Rydberg equation here. That's for calculating the energy levels of the hydrogen atom or any other atom that has 1 electron only. So remember, Z is your atomic number, N is the energy level. And these are the actual energy levels. These are all going to be negative because a negative potential energy means there's an attraction still between the proton or the electron and the nucleus, which is different from the transitions. So make sure you know how to take 2 of these energy levels and subtract between the 2 to find the difference in energy for your atom or for your photon, and how to calculate the energy of the photon that comes off, and how to calculate the wavelength of the photon that comes off. I know what that's supposed to be, I'll have to look it up. But this is for Coulomb's law, this is for speed of light, this is Planck's constant. I noticed that some people didn't quite know what some of the constants were. So make sure you know what they are. You don't have to memorize the numbers, you just have to know that this is Planck's constant. This is the speed of light. Okay, probably Coulomb's law is missing there. Anyway, so starting from the beginning, which transition in the hydrogen atom, in the spectrum of the hydrogen atom results in the emission of light with the strongest wavelength? So you have to have a vague idea of what the hydrogen energy levels look like. So going from low to high, the lowest is down here. These are all negative. Remember, 0 is up here somewhere. And then you get 2, and then they get 3, and this is approximately how they look. They get closer and closer together. We want an emission. An emission is only going to happen when an electron starts from a high energy and it drops down to a low energy. We want an emission with a long wavelength. Long wavelength means low energy, right? The larger the wavelength, the lower the energy is going to be. So we want the smallest transition, right? Low energy. So we can cut out D and E because D and E are absorptions. Those will not do emissions. That is the atom gaining energy. We want the atom losing energy. So it spits out a photon. So the 5 to 4 one looks pretty good to me. So remember, as you go higher in energy level, the gap between each subsequent energies gets smaller and smaller and smaller. So this transition here, 5 to 4, that is the smallest transition that's listed here. Compared to 3 to 2, compared to 3 to 1, which is the largest listed. Okay. So, circled. I can do this right. I did this on purpose. It's supposed to be easy. There we go. See? Okay. Now. Oh, I'm doing it in the wrong board. I don't have this one hooked up. Alright, if anybody's watching at home, hopefully nobody is. Alright, which of the following transitions in the spectrum of the hydrogen atom results in the absorption of a photon with the largest energy? So now we're going to a climbing transition. Alright, let me redo this so that people can see if they're watching recorded. So we want to go from a low to a high in this case. So E is out, D is out. These are going the other way. Those are emitting because they're going from high to low. So it looks like C, is it? Going from 1 to 4 will give you the largest change in energy when the atom absorbs a photon. So you hit this atom with a photon with a specific energy, this specific energy, it'll cause this transition. Okay, so that would be C. I can do it properly. There we go. All right. Questions so far? Nobody. What is the energy of light emitted when an electron falls from 4 to 2 in the hydrogen atom? So here we're looking at this transition. And honestly, you guys have done this in the lab. You've done this in homework. Maybe you've memorized it by now. But how do we calculate that? Or how do we figure that out? Well, we can use Bohr's equation for that. All right, scroll back to this thing right here. E to the n is equal to negative 2.178 times 10 to the minus, I wonder if that's not right, but maybe it is, minus 18 z squared over n squared. So we're looking at the transition between 4 and 2. Is that a problem? So we need to calculate what is the energy here and what is the energy here. And then we want to calculate the difference between the two. That's going to give us the energy. So z squared, this is a hydrogen atom. So z is 1. And, I mean, let's calculate energy level 4 first. Why not? So 4 squared is going to be 16. So whatever this is, and then we'll do the same thing for energy level 2. Writing. 1 squared over 2 squared. Let me grab my calculator. The first one, E4, minus 2.178, e to the minus 18, divided by 16. Is negative 1.36 times 10 to the minus 19. I'm going to leave the units off, and I'm not going to worry about sig figs right now. The second one is going to be over 4 instead, minus 5.445 times 10 to the minus 19. So we want the difference in energy, the change in energy between these two. And honestly, it doesn't really matter which way you go because you're just going to get a positive number in the end. But ideally, you would do final minus initial. That's what a change in energy for the atom is going to be. The final energy level is energy level 2. The initial energy level is energy level 4. And so if I plug those in, let's see. This minus a negative 1.36 e to the minus 19. I get a negative 4.085 times 10 to the minus 19 joules. This is for the atom. And so where does this energy go? This is a loss of energy for the atom. The energy goes with the photon. And so the photon is going to have, did I calculate something wrong? Let me see. Oh, I didn't see that one right here. Yeah, 4.09. There we go. 4.09 times 10 to the minus 19. So that's going to be the energy of the photon, A. Okay. So that's just like the lab, or just like, honestly, I think you guys have done homework like that. So, okay. The lab was actually a little different. The lab actually, you had the change in energy, and you had like E2, and you were calculating the missing energy levels. So you were not using Bohr's equation to calculate the missing energy levels. You were going backwards. Okay, which atom is represented by the shell model with 2 electrons in the first shell, 5 electrons in the second shell? So this is just, understanding how many electrons an atom should have. 2 electrons in the first shell, 5 electrons in the second shell. That's 7 total electrons. You can go straight to the periodic table and tell that that's going to be nitrogen. So that is nitrogen, just by the number of electrons they're talking about. You can follow the periodic table, and you can see that nitrogen also has 2 in the first shell, 5 in the second. So 2 in period 1, and then if you start in period 2, count over 1, 2, 3, 4, 5 the nitrogen. That's nitrogen. Okay. Arrange the following elements in order of increasing first ionization energy. So you have the trend going top to bottom. You have the trend going left to right. So sulfur and argon are in the same row. They're in period 3. Calcium is in one row below. So we know that as you go left to right, ionization energy increases. As you go top to bottom, ionization energy decreases. So calcium is going to have the lowest ionization energy. And that should make sense in your heads too, because metals are easier to ionize than nonmetals. Metals will lose their electrons more readily than a nonmetal will. So calcium is the lowest ionization energy. They're easiest to ionize. And then between sulfur and argon, as you go left to right, ionization energy increases. It gets harder to remove an electron as you go to the right of the periodic table. So sulfur is next, then argon. So it's E is the only one that makes sense. Yeah. So I'm not going to give you any grouping of elements that are just kind of hard to nitpick between. Like, they'll be pretty clear. This one is definitely lower, this one is definitely next, and this one's last, or highest. Okay. I warned you that you'll get questions like this before. 6. What period 3 element has these ionization energies? So you just have to kind of glance at them, and they're all ionization, so you removing an electron takes energy to do it. And okay, whatever, this takes this much energy. The next electron, the second electron removed, takes this much. And as you remove an additional electron, the ionization energy is going to go up, because you have the same number of protons still, but fewer electron-electron repulsions. So the remaining electrons are getting harder and harder to remove. And yeah, it goes up until you get to this one, and hopefully you can see that this one is a much, much bigger difference in energy. It's like climbing by 4 times, about. Whereas before it was just doubling about. And so this 6th electron, removing the 6th electron with the 6th ionization energy, is an inner electron. It's not from the valence shell. So only 5 electrons were in the valence shell. The 6th electron was in an inner shell. So this is something with 5 valence electrons, and from period 3, it has to be phosphorus in this case. Okay. Core charge. If you're dealing with a neutral atom, core charge is really easy to figure out. It's the same as the valence electron. silicon is group 4. It's got 4 valence electrons. The core charge is also going to be plus 4. You can calculate it manually if you like to. It's the protons minus inner electrons, but it is plus 4. That's an easy way to figure it out if it's neutral. Okay. So which atom requires the largest amount of energy? To remove the most tightly held electron, and there's a clue there, the electron closest to the nucleus. So this is a little bit different from what we normally think about. We think about removing the furthest away electron, the easiest to remove. That's the valence electron. Here we're removing the most innermost electron. So you have to think, well, what's happening at the innermost electron? There's no shielding anymore, right? There's no other electrons between the innermost electron and the nucleus. So that inner electron is experiencing the full whatever charge of the nucleus that it's feeling. So really we're looking for the element that has the greatest number of protons. That's the only consideration we're gonna look at when we're looking at how strongly attached is that inner electron. So out of all these 5, is it arsenic? It's like arsenic. AS. Yeah, arsenic has the highest atomic number. It's got the most protons, 33 protons. And so, I'm not saying that it has the lowest ionization energy. That's removing an outer electron. But as far as removing that innermost electron, the arsenic atom is going to be the hardest to do, because we're removing an electron that's feeling that full plus 33 charge from the nucleus. Okay. In which of the following groups of atoms does each atom have the same number of valence electrons? So, hopefully this is not a hard thing to do. You look at which atoms are in the same group on the periodic table. So, not boron, carbon, nitrogen. It's not potassium, calcium, phosphorus. It is carbon, silicon, germanium. All right, they're all group 4. They all have 4 valence electrons. The rest of them don't work either. Chem 222 is going to focus a lot on these group 4 elements. These are the more interesting ones. They're the ones that excluding carbon, you can work with as semiconductors. And even carbon is interesting because it's similar to those, for other reasons. But yeah, these are same number of valence electrons. All right, this is from a lab, but we've learned this. How do you calculate molarity? So remember that molarity is moles divided by liters. So ultimately, we need the moles of the solute, the moles of the stuff we're dissolving. We're going to divide it by the volume of the solution in liters. So the stuff we're dissolving is lithium bromide. I've got a mass, but I don't want it in mass in grams. I want it in moles. So we'll convert this to moles using a molar mass. So 1 lithium and 1 bromine, 6.941 and 79.904 is 86.845 grams per mole. I'll stop there, so I'll just calculate it. So 97.7 divided by that is 1.125 moles. It's not the right sig fig, but whatever. It's close enough right now. We're doing multiple choice. So now to find the concentration, well, we're dividing this solute by a volume of solution in liters. And I'm going to skip the step where I convert my milliliters to liters. But that 750 milliliters in liters is 0.750 liters. You divide by 1,000, basically. And there you go. Moles over liters is molarity. So 1.50 molar in the end. So A. And you got to go backwards too. So you've got a concentration, 3.000 molar. How many grams of NaCl are required to make? So I'm trying to find the amount of solute. That's the numerator part. I want it in grams though. So again, I warn everybody, whenever you see this big M, immediately change it into, instead of big M, it's moles per liter. That's what that unit translates to. And there is your conversion factor. So to get just the moles, I need to multiply this by a volume. That's the volume, 250 milliliters, but I need it in liters. So 0.2500 liters. Right? This will give me a mole, the moles of the solute. I want grams, so let's do an extra step. Let's multiply by the molar mass to get rid of the moles and get grams. And the molar mass of sodium chloride, 22.98977 plus 35.4527, 58.442.5 or so. That's enough. Sig figs. Do all that. 25 times 3 times the molar mass is 43.83 grams. Or sig figs. Yeah, there it is, D. So basically, if I wanted to make that solution, and I wanted to make a quarter of a liter, I would need to weigh out 44 grams of salt, and then make my solution like we made the solution in the lab the other day. And then it would be this concentration. All right. Oop. So, which of the following atoms has the largest size? All right, this is similar to the ionic ionization energy trends. So size, as you go left to right in the periodic table, elements get smaller, and as you go top to bottom, they get bigger. So sodium, potassium are in group 1, calcium and magnesium are in group 2, they're right adjacent. We're going to ignore group 2 because group 1 generally is bigger, and assuming it's from the same period. Potassium has its outermost electron in shell 4. So if I compare it to calcium, which also has an outermost electron in shell 4, the potassium is still bigger. As you go left to right, remember, you're only adding electrons to the same shell, but you're also adding more protons, so the extra proton shrinks the overall shell size. So potassium is the biggest. That is the biggest atom in this set. Okay, isoelectronic, 13. That is where they have the same number of electrons. So pay attention to the names. Sulfur versus sulfide, especially if it says sulfide ion. So if it's sulfide, we're talking about S2 minus. So it's sulfur, the normal ion that it forms is S2 minus. And so the sulfide ion is isoelectronic with, well, it's got the same number of electrons as argon does. So sulfur has 16 electrons, sulfide has 18, 2 extra, and argon has 18. And it's, I don't know why it's underlined, but there it is. Spell checker. Okay. Which two atoms do not form isoelectronic ions? So the idea is these are all neutral. If you turn them into their standard ion form, which ones would be isoelectronic, which ones wouldn't? We're looking for the ones that wouldn't be. So magnesium and nitrogen. So magnesium would form Mg2+, and Mg2+ would have not 12 electrons, it would have 10 electrons. Nitrogen would form N3-, right? You could add 3 electrons, and it would have 10 electrons. They would both look like neon. So they're isoelectronic. O and N, same thing. O makes O2 minus, right? You can know what charge they are from the group they're in. This would also have 10 electrons. Beryllium, however, beryllium is number 4. It's a metal. It's going to have a +2 charge when it forms an ion. And it would only have a total of 2 electrons afterwards. It would start with 4, you would lose 2 electrons, and you would have 2 left. So this one looks like helium. And so beryllium and nitrogen are not isoelectronic. Nitrogen as an ion looks like neon. Beryllium as an ion looks like helium. So it's C. These are not isoelectronic. And you can kind of prove to yourself that D is fine too. Which of the following ions is not isoelectronic with a noble gas? So all of these ions that we predict that you can make, excluding the transition metals, generally, they all look like some noble gas. That's kind of why they form these ions. And so if it's one of these normal ions that we normally predict, that's going to look like a noble gas. The only one that doesn't make sense up here is B, calcium plus. Calcium plus is not an ion we'd ever predict. I mean, if you look at calcium, it's in group 2. We would expect it to make a calcium 2 plus ion. That's the only way it looks like a noble gas. It's going to look like argon in that case. If it's calcium plus, it will not look like a noble gas. It's only missing 1 electron. It's going to look like potassium. So that doesn't fit. So the idea is it's not a normal ion. That's kind of the giveaway. You can count the electrons too and make sure, but it's just not one of our normal ions. Okay, let's get rid of this thing. Come on. Okay. So the following ions are all isoelectronic with neon, which has the largest radius. So now we're not doing the standard left to right, the smaller, top to bottom is bigger. These are all isoelectronic, so they'll have the same number of electrons. We compare them a little bit more different. So they have the same shell sizes, so they're still the same shell counts of electrons. So we then have to look at a different criteria, and that's going to be number of protons. If they have the same electrons, then really the protons is what's going to make them different. And the one with the largest radius is going to have the fewest number of protons. Right, the least number of positive charges pulling on those electrons. And so that's going to be O2 minus. It's only got 8 protons. It's going to pull very weakly on these 10 electrons that it has. Whereas magnesium 2 plus has 12 protons. It's going to be able to pull those 10 electrons a little bit more tightly than oxide would. It'll be smaller. Okay, so we're going to arrange these in order of decreasing ionic radius. All right, this is a tricky one. Gotta go a little slow. Put them in the different groupings if you have to. So we're talking about the regular ions for fluoride, chloride, bromide, and then sodium and lithium. So if we look at fluoride, chloride, and bromide, those are easy to group together. So fluoride, and we're talking about size. Out of all of those 3, fluoride is going to be the smallest. So fluoride is smaller than chloride, which is smaller than bromide. Let's do it the way they're doing, decreasing. So we're going to start with largest. The largest is going to be bromide. And then chloride is smaller, and then fluoride is the smallest. Okay. Let's do the cations next, so sodium and lithium. So we know that sodium is going to be bigger than lithium ion, just because of the shell they're in, right? Sodium has their second shell filled, lithium only has the first shell filled. Now, how do we merge these two? Well, let's look at isoelectronic things, right? These are not isoelectronic, these are not isoelectronic. They have different numbers of electrons. But Na plus and F minus are isoelectronic. Electronic, I can spell today. Electronic. So between sodium plus and F minus, which one is smaller? Yeah, it's the fluoride. The fluoride is going to be the smaller one because, no, I'm sorry, the other way around. The smaller one is going to be the sodium because it has more protons. Sorry. So yeah, so this one is the smaller one. Alright, this is the bigger one. Alright, because sodium has more protons. They have the same number of electrons, but sodium has more protons, so it's going to be smaller. Okay, well, that would mean that the order goes bromide, chloride, fluoride, sodium, lithium. Yeah, so it's A. Yeah, we're going smaller. The less than greater thing always throws me off for a second. I've got to look at it a couple times. But there it is. That's the one that makes sense.
Wait, wouldn't it be E?
Did I get it wrong? Hold on.
Oh, your D would be D.
Oh, I'm sorry. You're right. B are, sorry, you're right. Sorry. Yeah. Don't do it too quickly. There we go. B. Bromide, then chloride, then fluoride, then sodium, then lithium. Okay. That's it. That makes sense. Okay. So the number of valence electrons in bromine is B, 7. I mean, this is yet another question asking you the difference between valence electrons and total electrons. It's got, I mean, even the total electrons are not even there. So, 19. The quantum mechanical solutions to the Schrödinger wave equations are called. So, the answer here, the only one that makes sense, is wave functions. So, these are the solutions to the Schrödinger wave equation. After you plug in your quantum numbers, you get these wave functions. And the wave functions can be used to kind of build your orbitals, to describe your orbitals. That's pretty much the meat of what you needed to get out of that quantum mechanical chapter. That and Heisenberg stuff. And the quantum numbers. So, 20, the Pauli exclusion principle states that. So there's two versions of this. There's the easy version, and then there's the more complicated version. The easy version is the Pauli exclusion principle is that you must have opposing spins in the same orbit. But really, the large version, the real version of the Pauli exclusion principle is that no two electrons can have the same 4 quantum numbers. So every electron has to have a unique set of quantum numbers. So no two electrons in an atom can have the same spin. That's wrong. It's in an orbital, not a whole atom. No two electrons in an atom can occupy the same orbital. Yeah, you can have 2 electrons in one orbital. They just need to be opposing spin. 2 electrons in the same orbital have identical values of spin. No, that's opposite. No two electrons in an atom can have the same set of core quantum numbers. That's it, D. That is the full version of the Pauli exclusion principle, is that no 2 electrons can have the same set of quantum numbers. Okay. What is the element with that electron configuration? So you can kind of ignore everything but the valence electrons. So you can ignore these and just look at the 4s2, 3d10, 4p4. So we're starting in period 4, going past the S block, past the D block, going all the way to the P block. And if I count over 1, 2, 3, 4, that is selenium. So selenium is in group 6A, D. is the correct condensed electron configuration for titanium? So titanium, condensed. We'll start with titanium on the periodic table. Go back a little bit. Argon is your first noble gas that comes before titanium. So titanium's in row 4, so we're going to start with the 4th shell, S block, and we're going to fill that up with 2. And as I continue counting over to get to titanium, well, in the D block, I just have to count over 2 elements in the D block. But remember that the D block starts at 3D, not 4D. So it's 4S, then 3D, 3D2. And so it looks like E is it. Okay, E works. So what is the correct condensed electron configuration for the phosphorus 3+ ion? It's a little bit of a trick. I'm not saying it's a trick question exactly, but if you are doing this really quickly, you might assume phosphorus 3-, which is the standard ion phosphorus would take. But it's phosphorus 3+. So, I mean, we can just, let's be safe. Let's do phosphorus normally. Regular phosphorus, it's in row 3. We go back. The first noble gas that comes before it is neon. And then on row 3, we do 3s2, and then 3p phosphorus 1, 2, 3. Now, if this was p3-, we would add 3 electrons. It would look just like argon. But this is p3+, which means we're missing 3 electrons. And so which 3 electrons are going to go? They're going to be the highest, in the highest subshell, which is going to be the 3p. So phosphorus 3+ is going to be a neon core with 3s2, and that's it. Those 3p, these 3 electrons in the 3p subshell are gone. We don't write an empty subshell. So it's a B. Okay. 24. So 24, how do we want to do this? Okay, let's just do 24 normally. So 24 is tin, and it would help to start with the electron configuration of regular tin first before we do the tin ion. So tin is in row 5. Krypton is the noble gas that comes right before the row 5. And then after that, it's 5s2. We're filling the whole D block, 4d10, and then 5p2. That's regular tin. Now, tin is not a transition metal. So the last thing we learned in class last week was that for transition metals, we remove the s subshell first, electrons. But this is not a transition metal. We have these electrons to remove first, the p ones. So tin 2+ is going to be the exact same thing with those p electrons gone. What's another ion for tin that's common, do you think? So tin comes in various ions. It's one of the exclusions. Like you can, it's a type 2 metal. So if I took, for instance, these 2 electrons away, I would have a filled D block, D subshell. And that's actually pretty stable too. So tin 2+ and tin 4+, these are really common ions you see in the world. Anyway, this is the answer to this one though. D. Missed a little bit. There we go. Okay. Stop me if you don't understand something, please. Which electron configuration for carbon would satisfy Hund's rules? So now we have an electron configuration that's not really an electron configuration. It's more like an orbital diagram now. because we have the individual orbitals separated out. So that's fine. We just have to show the position of each electron now. For carbon, and let's do it with boxes instead. Here's your 1s, here's your 2s, and here's your 2p's. Carbon has 6 electrons total. So you're going to have 2 here, 1, 2, 3, 4, and then you have 2 more, 5 and 6. So that's Hund's rule in action. You have to put 1 electron in each degenerate orbital before you can pair them up. And so the only one that makes sense is probably B. You've got 2 in the first shell, first S subshell, 2 in the 2s subshell, and then 1 in each of the p orbitals. In the first 2 p orbitals. That's it. So B. This is the only one that kind of works. The other answers are either electrons in the wrong place, like A, or too many electrons. C and D is too many. All right, which atom or ion has the largest number of unpaired electrons? So you kind of have to do the orbital diagram. Kind of similar to what we did here. So this is carbon. Let's do C, carbon 4 minus. So carbon 4 minus means 4 extra electrons. So if I draw those in, 1, 2, 3, 4. No unpaired electrons. All right, what about lithium plus? I can tell you lithium plus is all, here. Lithium plus has only 2 electrons. Lithium normally has 3. Lithium plus means 2 electrons. No unpaired electrons. Boron. So boron has 5 electrons. So 1, 2, 3, 4, 5. 1 unpaired electron. Nitrogen. And until you're used to these, you just have to draw them out. So nitrogen has 7 total electrons. 1, 2, 3, 4, 5, 6, 7. So 3 unpaired electrons. I'm going to skip E. I'm going to tell you E looks exactly like this one. It's full subshell, everything. So nitrogen is the winner. Nitrogen has the largest number of unpaired electrons. Okay. So don't forget to get used to counting total electrons and then filling them in the right number, in the right orbitals. Okay, so we have a set of quantum numbers. Most of them are good. No, actually, most of them are bad. There's only one that's good. So which set is allowed? So you kind of have to go through for every one and just see what's allowed. So let's start with energy level 4. So every one of them has energy level 4 as the starting quantum number. N is equal to 4. That's okay. So now that we know n is 4, we have limits on what the next quantum number can be, right? L is every integer from 0 up to n minus 1. So if n is 4, n minus 1 is 3. So all the values 0, 1, 2, and 3. Those are allowed if n is 4. And if you look, that's not allowed. Minus 2 is not allowed. So this one's out. A is no good. The rest of them are okay. They fit those rules. All right, well now it's the tedious part. We've got to try each one of them. So let's try L is 2, and let's see what comes next. So if L is 2, then M sub L is all the integers between positive L and minus L. So it's 2, 1, 0, minus 1, minus 2. So if L is 2, excuse me, M sub L, there's no way it can be 3. So that B is out. The last one, E, if L is 2, m sub L2 is fine. But I'm really quickly looking at this thing. M sub S, the last quantum number, there's only 2 allowed numbers, and it doesn't depend on anything else. It just has to be +1/2 or -1/2. So that M sub S2 on E, this last one makes it invalid as well. Okay. We could check L is equal to 3. We could check L is equal to 0. These are going to work. I could quickly zero in on another thing that's wrong. This M sub S on C, the last quantum number, is also bad. You can't have M sub S as 1. M sub S has to be +1/2 or -1/2. So the only one that works is D. And just to make sure, if L is 0, which is what the second quantum number on D is, M sub L can only be 0. Everything from -L to positive L, so that's 0. That's it. And your M sub S can be +1/2 or -1/2. That's it. And they all fit. So D is a good one. All right. That was a fun one. Okay. Which of the following quantum numbers is used to describe the subshell of an orbital? So this is what they mean. Shell is N. Subshell is the L quantum number, right? L0 means S orbitals. L1 means P orbitals. L2 means D orbitals. L3 means F orbitals. So L is the one used to describe the subshell. There's not much I can say beyond that. M sub L is for the orientation, so which way it's pointed. It also tells you a little bit about how many. And M sub S has nothing to do with the orbital at all. M sub S is just the spin on the electron itself. All right, 29. Which set of quantum numbers can be used to describe a 2p electron? So, this is basically going back and forth between this quantum number idea and our subshell model. A 2p subshell means that n was 2, and L, since the p orbital, was 1. That's really the biggest requirements, and everything else has to just work. Everything else has to be an allowed number. So 2 and 1 are the only values, so we can get rid of pretty much everything but A. A works. The M sub L values, 0 is fine when L is 1, right? So M sub L can be 1, 0, and -1, and M sub S always +1/2 or -1/2. That's it. So A works. Okay. What is the maximum number of electrons that can be accommodated in the subshell for which n is 3 and L is 2? The 3 part actually doesn't matter so much. Not at least not for this problem. The L part is what matters. So L2, we're talking about d orbitals. So L0 is S, L1 is P, L2 is D. So if you have d orbitals, how many d orbitals are there generally? There's 5 d orbitals. And 2 electrons per d orbital, that's 10 electrons. If you want, another way to think about it is d orbitals, look at the d block. There's 10 elements in, there's 10 groups. So there's going to be 10 electrons. So the maximum number of electrons that you can put in that d subshell is 10. Another way to think about it, again, d orbitals always come in sets of 5. So if that was this is the 3D subshell, you can put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in there. Okay. Which of the following sets of quantum numbers could represent the single orbital represented in this picture here? So you have to identify what it is first. This is very, very much a p orbital. All right. One of the reasons I know it's a p orbital is I count 2 lobes. The other reason is they're literally showing you the nodal plane, this little plane that cuts the two nodes in half where it doesn't hit any electron density. And p orbitals just have one nodal plane. Anyway, the two lobes should be enough. This is a p orbital. So the only thing we're restricted by is that L has to be 1. That's p orbitals. L has to be 1. So the only thing that fits that is C. I don't really know what shell it's in, because I mean, generally p orbitals look all the same to me. But this is the only one that fits. Although,
Would it be
oh, I'm sorry, I didn't see that one. So I only saw this one here. So between A and C, they both are p orbitals. But the m sub L, I saw that, I was like, wait a minute. The m sub L doesn't fit. When L is 1, where is it? When L is 1, the only m sub L values you can have are 1, 0, and minus 1. So you cannot have a minus 3 m sub L. So that's out. It's A. Yeah. Sorry for that. Thank you. Okay. 32 has perplexed lots of students in the past. So let's talk about 32, which is the largest. So we've got 3 versions of lead. We've got neutral lead, we've got the cation, which is normal, and then we've got this weird anion. And some people are like, well, since the anion can't really exist, I'm going to ignore it. Don't do that. You can forcefully make it, but what would the size be? So I think if you think about between regular lead versus the cation version, well, what is the difference? Well, this has fewer electrons, so less electron-electron repulsion. They both have the same number of protons. If you think about where those 2 electrons are coming from, they're coming from one of the p shells, so you still have the other subshells. So it's not going to get drastically smaller, but it's going to get smaller because of the less electron-electron repulsion. All right, so this is smaller because of less electron-electron repulsion. If you want to do the shell model, you can try to map that out, and you'll just see it's the only thing we can look at is it's got the same number of protons, just fewer electrons. But then let's add this thing to the mix. This means a lead with 2 extra electrons. Those 2 extra electrons, it's going to make it look like polonium, but it's not going into a new shell or anything, so it's not obviously bigger. But more electrons means more electron-electron repulsion. It's got the same nuclear charge, so that's not making it smaller. It's just going to get bigger. So this is actually going to be the biggest. Pb2 minus is the biggest. And so, this is where your knowledge comes in, not just memorizing trends. You have to understand why things are bigger. Okay. So far, so good? I think so. So some of these are kind of essayist questions, which were very difficult, more difficult to grade when you guys were doing remote stuff, but we can do these a little bit easier in person. So a hydrogen atom contains only 1 electron, but there are many lines in the emission spectrum. How does the Bohr model of the atom explain this? To get full credit, you should explain that the lines come from transitions of an electron between energy levels. So you can't just say, oh, there's many energy levels, because it's not the energy levels that's causing the lines. The lines come from the electrons transitioning between the energy levels. And so I'm not going to write that out, but it's some version of what I just said. All right, so talking about those transitions, that's the important part, not just the lines, not just the energy level, it's the transitions between them. And it would help to explain its high to low. When an electron is in a high energy level and it transitions to a low energy level, the atom has to lose that energy, and it loses that energy by emitting a photon. Okay, So one of the lines has this photon energy. What is the wavelength of this photon? So, you know, you have to pick out the equation that makes sense. We're looking for, I mean, they're giving us the energy of the photon, and we need the wavelength. So that's where this equation comes in handy. Energy of a photon is equal to hc over lambda. Now, on the instruction sheet in the front, I think I only gave you this equation. Energy of a photon is equal to h frequency, h nu. And I also gave you c is equal to nu lambda. You can combine these two together to get that if you want. So solve for frequency here. Divide both sides by lambda. You get frequency is speed of light over lambda. And then I'm going to plug that in place of here. And you end up with energy of a photon is equal to h times c over lambda. You get exactly what I wrote there. So in case you need to derive it yourself, there you go. Color, or wavelength. Well, I'm going to swap these two positions. So multiply both sides by lambda, divide both sides by e. I end up with this. And then I solve. So Planck's constant, 6.626 times 10 to the minus 34 joules seconds. Speed of light, 3.00 times 10 to the 8 meters per second. And energy of the photon, make sure it's in the right units. This is in joules, that's in joules. Perfect. 4.087 times 10 to the minus 19. If it's not in joule, if it's in electron volts or something unusual, convert it. I will give you conversions. You don't have to know those. You just need to know the basic metric conversions, like kilo to regular units, something like that. All right, so what is this? 6.626 e to the minus 34 times e to the 8, 3 to the 8 divided by 4.087 e to the minus 19. Here's another one that we've done so much that you can almost memorize it. So this is 4.86. Let's use a fourth sig fig times 10 to the minus 7 meters. And then to convert to nanometers, well, no, we could leave it like that for now, but then you would want to know what color is it. So if you scroll back, we've got our little chart here. This chart here is in nanometers. So let's convert it to nanometers so we can line it up with this chart. So 1 of the prefixed unit, what does nano mean? Nano means 10 to the minus 9. And so this gives us wavelength is 486.7 nanometers. And that is pretty blue to me. That's more subjective, but yeah, blue, bluish, something along those lines. All right, long way to go. All right, use the concept of core charge and distance to explain these trends. So this is understanding why these trends work, and be able to explain how it happens. The atomic radius as you go across a period and down a group. So let's go down a group first. Why does radius increase as we go down a group? And let's use core charge to do it, or core charge and distance. So let's pick two elements, sodium and potassium. Why not? Doesn't really matter. You can pick any two as long as they make sense for your explanation. So if I do the core charge model for sodium, it's going to be a +1 core charge with a single electron. Sodium is going to be a +1 core charge with a single electron. They look identical until you remember that this is shell 3, and then this one is shell 4. These valence shells are different. So this electron is further away than this electron. And there you go. There's one explanation for why, as you go down a group, the atoms get bigger. Because the electrons, the valence electrons are in a further away valence shell. Yeah?
So for the test, would you want us to draw out all the shells?
You can explain it if you want. You just, so the idea is try to use core charge and distance to explain why.
Okay.
So now as we go across a group, so let's pick two atoms that go across. Let's do sodium and magnesium. You could use anything. So again, we have sodium, +1. And this is shell 3. Magnesium is going to be a +2 core charge with 2 electrons. And if they're both shell 3, it's not distance anymore that determines how big they're going to be, because they're approximately the same size in terms of where their shells are. But the +2 core charge is going to pull a little bit more strongly in those shell 3 electrons than the +1 core charge will. And so it's going to shrink the shell by a little bit more than sodium would because of the higher core charge. And so because of the higher core charge, this is smaller. Right? It makes the shell a little bit, pulls the electrons in the shell a little bit closer than normal. And so now we can explain the same thing, but let's explain ionization energy. So as far as size goes, we've got that explained, but for ionization energy, you can still use distance. You can still use core charge to do it. So for ionization energy, I'm going to explain it in detail. You can paraphrase it however you like. But remember that ionization energy is equal to the opposite of the potential energy. And the potential energy is Coulomb's law. We can use Coulomb's law to describe it. And the idea here is, if the charges are exactly the same, that's what Q1 and Q2 are. So we're using the core charge as the inner charge. We're using the electron -1 as the sec Q2. And the distances are, well, the core charges are the same. The distances are different. This electron is further away. A larger distance means a smaller or closer to 0 potential energy. And so it's going to have a smaller ionization energy as a result. Or you can just say it's further away, it's less attracted, easier to remove, so it takes less energy to remove. However you want to say it. If you like to say it the mathematical way, or just the, explaining in terms of energy, and that's it. For sodium versus magnesium, an electron held on by a larger core charge, so if Q2, the electron is -1, but the Q1 is +2 now instead of +1, it's going to be held on with a tighter potential, a lower potential energy, a more negative potential energy. And the more negative the potential energy is, the higher the ionization energy is going to be. So this is a harder to remove electron because it's more tightly held on because of that charge. So it has a higher ionization energy. So higher ionization energy, higher ionization energy. All right, I wish I had split it up into 2 different sections, but whatever, it's fine. All right, I'm not going to have this many explain questions. At least I don't want to. I don't like grading them that much. And I know you guys don't like grading them either. All right, this is an interesting question. So this is, here, let me scroll back up. Let's say you're in a different universe, and everything works differently there, including the shells, all that stuff. So we examine the ionization energies of the random elements. So element 1 has this ionization energy, element 2 has this, and they're named differently, of course, because it's a different universe. Let's kind of explore what would happen if this was the data that we have for this universe. So, question A, how many electrons are required to fill the first shell of an atom in this universe? So, how did we do that for our atoms? Well, we looked at the ionization energy, and if you go to more and more electrons, and more protons, the ionization energy goes up. So it goes up, and all of a sudden it drops. And remember, when it drops, that's because you're adding an electron to a new shell. And that shell is further away, and so that further away electron is easier to remove. So in this universe, it only drops after the third electron. So the idea here is, in this universe, the first shell has spots for 3 electrons, not 2. Okay, and that's because as you're adding electrons, they continue to go into the first shell. And that's why the ionization energy increases. They're at the same distance. But why is the ionization energy increasing? Because the protons are increasing too. And it only drops when you get to shell 4. Even though there's another proton, it drops because that 4th electron is further away. It's in a new shell. So this thing has 3 electrons in the first shell. Let's organize everything. So room for 3 electrons is shell 1. All right. How many electrons are required to fill the second shell of an atom in this universe? Well, here's the start of the second shell. We add electrons, and this ionization energy goes up, and up, and up, and up, and all of a sudden it drops again. So if you count 1, 2, 3, 4, 5, 6, after the 6th electron, the 7th electron, the 7th electron's in a new shell. So you can fit 6 electrons in the second shell, according to the ionization energy data. Okay. So what is the core charge of an element if the atomic number is 6? Okay. So this is where we get kind of abstract. So how do we do core charge? So the shortcut was, same valence electrons. But let's do it the original way. It's going to be the number of protons minus inner electrons. And so to understand how to do a core charge, let's do the shell model for element 6. So an element that has 6 protons in this universe would have 6 electrons. And where would they go? Well, the first shell has room for 3 in this weird universe. And then the second shell has room for 6, but we only have 3 more. We put 3 here, and then there's the 3 more. They'll go right there. So that's the shell model for this thing. Now, how do we do core charge? Core charge is going to be the number of protons minus the number of inner electrons. So this is our valence shell. These are the only inner electrons we have. So 6 minus 3, and we have a core charge of plus 3. Okay? So far so good? All right. How many valence electrons does that same element have? 1, 2, 3. And if you didn't draw it, you could, the core charge is the same. Okay. What's next? Draw a shell model diagram for element 10. Okay. So element 10, Z is equal to 10. That means it's got 10 protons and 10 electrons. So first shell has room for 3. Got 7 electrons left. Second shell, well, we already answered, has room for 6. So I'm going to use all 6 spots. I've placed 9 electrons. I've got 1 left. 10 electrons total. So the last one must be in the third shell. There we go. There's our shell model for our fictitious element 10 in this weird universe. And I think there's one more. Yeah. Draw a diagram showing the shells and placement of electrons for element 10 using the core charge model, core charge concept. So this is the shell model. For core charge, we're going to calculate the core charge first. It's 10 minus the number of inner electrons. So This is our valence shell. That single electron is our valence electron. Everything else is an inner electron. 1, 2, 3, 4, 5, 6, 7, 8, 9 inner electrons. So the core charge is +1. So I'm going to draw a core charge of +1, and then in our core charge concept model, we only show the valence shell. So there's our third shell. Just label it just in case, with the 1 electron in it. That is the core charge model for this fictitious element. So which of these 10 elements would you expect to be largest? Okay, we're going to stretch our imagination a little bit. So how do we figure out size to begin with? Well, the number of shells it has will kind of tell you about the size. So this one's already pretty big. What else do we have? I think that's it. Yeah, so element number 10. It's the only one with an electron in shell 3. So out of everything here, it's element 10 is the biggest. If there was an element 11, and that 11th electron went into this same shell, which one would be biggest, 10 or 11? It'd still be 10. Because now we're at, when you remember, as you go left to right in the periodic table, you're adding electrons to the same shell. You're also increasing the number of protons, and so all that's doing is it's causing the shell to shrink a little bit from the extra protons. So yeah, element 10 is the biggest. Yeah, if you look at all the elements on shell 2, looks like RQ is the biggest. And all the elements in shell 1, it's AB is the biggest. All right, and that's it for that. Oh, which is the smallest? We didn't answer which is the smallest. So, which is the smallest? Out of these 10 elements, which is the smallest?
3.
Yeah, it is 3. So first we're going to pick an element that has only one shell. So that's one of these 3, because we're filling only the first shell. And we want to, like on the periodic table, between hydrogen and helium, helium is smaller than hydrogen. Because you're filling the same shell, but now you have a second proton, and so the electron cloud is a little bit smaller because of that second proton. Well, that's what's happening with this element here. You've got 3 electrons, but they're all in the same, that first shell, same as this one, and this one, but it's got 3 protons. So that 3 proton is causing that first shell to shrink a little bit more than the others would be. So FT is the smallest element. All right. I like this is a good problem because it kind of tests your everything we learned so far in this class. Any questions on that one, real quick, before we move on? Okay, got some time left. So arrange these ions in order of decreasing size. Which noble gas is each ion isoelectronic with? So don't assume that the ions that I give you are all isoelectronic with each other. Verify that they are or not. So Se2 minus. I mean, one way you can verify is just count electrons. So Se has 34 electrons normally, selenium. So Se2 minus has 36 electrons. Bromide has 35. Bromide would have 36. Rubidium plus. So rubidium has gotten 37 normally. So rubidium plus also has 36. And then strontium 2 plus. So okay, they're all isoelectronic with each other. They all have 36 electrons. They're all isoelectronic with krypton. Krypton is the noble gas that they are all isoelectronic with. Now let's arrange them in order of decreasing size. So if they're all isoelectronic, it's easy. You pick the one with the most protons is going to be the smallest. And so the one with the most protons is strontium 2+. This is the smallest, in order of decreasing size. So this is the biggest. And then bromide, and then rubidium, and then strontium. Yeah. And if you wanted to fit krypton in there, it's right in between here. But all right, so verify they're isoelectronic before you go with the problem, unless the problem tells you that they're isoelectronic. The way it's worded is not clear. Ooh, okay. Photoelectron spectroscopy. So looking at that, what is the full electron configuration for the element that would give us this electron, this PES or XPS? So this is showing everything. So you can probably assume that the highest energy peak is going to be the innermost subshell, the 1s. So that's the 1s. And if it's full, usually is, if it's in the inside, it's got 2 electrons in it. So this height corresponds to 2 electrons. So that's 1s2. Next comes something else with 2 electrons. It's a 2s. After that comes something that is 3 times the height. 2 times 3 is 6 electrons, so that's the 2p. This is all going according to how you memorize the, or you learn the subshell order. After 2p comes 3s, which makes sense, it's got 2 electrons in it. After 3s comes the 3p. And what comes next? What's the last peak? 4s, not 3d, 4s comes next. And it's only got 1 electron in it because it's half the height of the s subshells, or the other s ones, I should say. So that's the electron configuration for this thing that we get from this photoelectron spectrum. What element is it? Yeah, it's potassium. And you can just zoom in on that part. 4s1, that's potassium. Group 4, 1 electron of 1, it's the first one. Okay, what orbital diagram can we draw for this? So, I'd probably be more specific on the actual exam, but if you want to do just valence, that might work. So let's do the whole thing, just to be clear. So in orbital diagram, you would just do this. 1s, 2s, draw the separate boxes for the p's, 3s, 3p, and then 4s. And that's it. And then, well, you fill them. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's the orbital diagram. Now, an energy diagram is exactly the same as this. It's just showing it on an energy plot. So, kind of show where they are on the energy axis. You don't have to use boxes if you want. You can use boxes. You can use lines, whatever you want. But basically, you're going to just sketch this out exactly the same way. The 1s, and there's the 2s, and then there's the 2p's, and there's the 3s, and there's the 3p's, and then there's the 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19. A lot of arrows to draw. Okay. Nope, we're done. Not done yet. So write the full electron configuration for nickel 2+. And I think then we're done. We've done a little early today. So, this is the last thing we talked about in last week. This is a transition metal, so nickel is right there, right smack in the middle of the transition metals. This is one you don't normally, you can't automatically predict the ions that it forms because it makes multiples. So if it was nickel 2+, what is the electron configuration? So let's start off with plain nickel, the neutral one. And we can do the condensed version. Argon is kind of how it starts. It's the noble gas that comes with 4 nickel. And then after argon, we're in row 4. And we start with the S block. That's full. After the 4s comes the D block. So we have this row of D elements. But remember, shift down 1 shell. 3D. And then count over 1, 2, 3, 4, 5, 6, 7, 8 to get to nickel. So 3D8. That is the electron configuration for plain neutral nickel. So what if we make a cation out of it? If I remove 2 electrons. So this is the one thing you have to remember. This is different for transition metals. Instead of removing the highest energy, which is normally what we do for main group elements, we're going to remove the S subshell electrons first. So we're removing 2 of them. So both of these come away. And so nickel is argon 3D8. And that's it. So that's nickel 2+'s electron configuration. Like I said, I showed you all the interesting things you can get out of this, but we're not going to quiz you on that. It's just writing that, understanding that those electrons come from the S subshell. Alright. I wonder if they're compliant or something like that.
Is it orange vest people?
Yeah.
Yeah, they are.
They're just checking masks and stuff.
Yeah, I get nervous in my public speaking class because every now and then if they come around and they're like,
okay, that's fine.
yeah.
I don't mind. I just never knew what they were for. Okay. So that's it. I went through the process exam a little bit quickly, but I think that's all we have left. Yeah, that's it for that. Besides that, let me pull up the review sheet. I think this is the one I posted to you guys to D2L. Yeah. So, make sure you go over this stuff. These are the connectivities. I think we covered pretty much everything. So, understanding the hydrogen energy levels and how to calculate those photons. That's one thing. Then there's all the shell model, core charge model stuff, photoelectron spectroscopy, all the trends you get from that. So like figuring out size, figuring out ionization energies. And then is just the link between that older model and the quantum mechanical model, which is really just understanding how the quantum numbers fit in. So how do you relate quantum numbers to the shell stuff that we learned? So then it's just a few conceptual things, and that's it. Electron configuration. So, I'm making it seem like there's not much. There is a lot to go over, but I feel like the topics are more tightly, they're more limited, let's put it that way. Or more focused, let's put it that way. Because like last test, there's a lot of different random stuff. Alright, I think you've gotten back most of your labs. I think there's people that came in a little late. Make sure I give you back your stuff before you leave. No quiz, obviously, so we'll have our exam on Wednesday instead. But, yeah, make sure that your quizzes that you get back make sense to you. If you're not sure what you did wrong, let me know and we can talk about it. I have lab tomorrow morning for my other class. They have lecture after lunch. But you can always come by if you need and interrupt the lab, or not interrupt, but just come and talk to me during lab. There's just lots of free time then. Other than that, you guys have lab in the morning on Wednesday. It's your guys' turn to have a lab before your exam. The last class did it last time. So, yeah, we have some time in the lab also to ask questions. I think that the lab itself is not long. The write-up is a little bit harrowing for the lab that we're going to do this week, but the lab itself is not too bad. So there should be time to like take breaks and go study, have a good lunch before you start your thing. Okay? All right, any questions?
it only transition metals that you remove the inner shell first?
Yeah, yes. So just the transition metals. So the one we did, the tin, we would remove the P block first. That's the highest energy subshell electrons. But after that, then it starts acting like a transition metal, and you remove the S, but we're not going to go over that. That's too far advanced. So yeah, just look at, is it a transition metal? If it is, we'll remove the S block electrons first.
Thanks.
Yeah.
What would the electron orbital diagram look like for nickel?
Okay. Do you want to do the whole thing, or?
Oh, the one that has the E and then the arrow going up.
Oh, yeah, okay. Well, I mean, I guess all the inner shells too. I guess we can do that. So 1s, 2s, 2p, 3s, 3p. So you want to do nickel 2 plus, right? Not the.
Oh, the regular nickel.
Regular nickel. Let's do
Yeah, I'm
regular
trying
nickel.
to see why it takes the inner shells first.
Okay, well, that's going to be interesting. So let's do that. So after 3p, the 4s comes here, and the 3d is like just a smidge higher than the 4s. Like almost, like you can measure it, it's different, but you know, if you were to compare the difference between like this and 4s and 3d, they're a lot closer. So for normal nickel, 4s comes first, and so when you fill it, fill all these really quick. Okay, then it goes 4s2, 3d, 8. Alright, that's normal nickel. And let me exaggerate even more, so it's actually a little bit higher. So you can really see that 3d is higher. Now, what the short version is, when you ionize nickel, the electrons from the 4s subshell are suddenly gone. But here's what's really happening. You are actually removing the highest energy electrons, which happen to be these. Okay? But as soon as you remove these, the entire shell, or the entire subshell, goes down in energy. It goes a little bit lower. And when that happens, then these electrons are in a higher subshell, and they don't want to be. They'll instantly move back over here. And that's why, at the end, your 4s is empty, and your 3d has all of its electrons still. Is that going to make sense?
Yeah, no, that makes sense.
So yeah, when it's neutral, the 3d subshell is higher energy. But when you take away those electrons, the subshell energies all over the atom change. All of them change, but the way they change is the 4s and the 3d kind of swap positions almost. And now you want to have the ground state. So the electrons want to be in the lowest energy state possible. So they're going to go to the lowest energy subshell as possible.
Okay.
So yes, the electrons technically come out of the 3d first. But then everything rearranges so that these electrons then move back to the 3d, and so now it's the 4s ones are gone.
Okay.
Yeah. But ultimately just remember, oh, well, just take away the 4s electrons. That's probably the easiest thing to remember. Okay. I forgot to switch my mask. This thing's fogging up my glasses like crazy. Any other questions? Yeah.
Is there a late penalty if we keep today's homework to studying?
I'm fine with that. You can keep it. If you want to take it back, feel free. Labs are a different story, but yeah, I've been kind of lenient for homework. You get the biggest pile of unaccepted stuff.
Goodness.
So if you have questions, let me know. I'm gonna hand this out while you guys are still here. These are homework? Those are homework, yeah. Thank you. Alright, hopefully there's no objections to having an early end. Alright. I'm happy to stick around if you want to go one-on-one for some sort of stuff, but yeah. Good job.